Okay, so we're continuing on in Chapter 10. The Chapter 9 problems will probably be due next Monday. And then we'll have the Chapter 10 problems due later in the week. I haven't gotten that part of the Canvas site updated yet. So you should it's going to kind of be self-paced as you're going through them. If you're waiting for the last minute to do those, then I hope you better have a subscription to Chegg to get the answers. I don't think these are on Chegg yet. When they do, I get my legal team and we own Chegg. But just kind of work through them. The way it looks like Chapter 10 it looks like Chapter 11 is kind of a mixture of SN1, SN2, E1, and E2. And so we'll have some problems. We'll go through some problems there, and I do have, I think, at least one day of problem sets that I could give you where we can work through them. That may be Friday. Well, actually, no, it won't be Friday, because we'll finish up E2 on Friday. And I put a video in front of E2 that's going to do what I'm going to do today. But since it's late, probably nobody watched it, which is fine. You can go back and take a look at it along with today. So E2. Anybody have any questions about E1? I'm going to go back and kind of review E1 in the context of E2. All right, so E2, the 2 means bimolecular. And so just like in SN2, it's going to be bimolecular kinetics, no carbocation. And so let's, for instance, let's use the same molecule that we did, I think, on Wednesday or on Monday, which is, let's take 2-chlorobutane. And let's do an E2 reaction on this instead of E1. So in E1, we'd break the carbon-chlorine bond, we'd form the carbocation, we'd lose H+. If we're just writing the products of this reaction, we find the alpha carbon, we find all the beta carbons, and make sure that they have beta hydrogens. And in this case, there's 2 sets of beta hydrogens that could be lost. Call them HA and HB. So in terms of writing the product of this reaction, product A would be having the double bond in the 2 position. And having product B would be at the end, depending on whether I lose beta hydrogen A or beta hydrogen B. Okay. And we'll go through the mechanism of this E2 in a minute. So writing the products is exactly the same. Find the alpha carbon that has the leaving group, the 2 beta carbons. If they have beta hydrogens, then those can be lost to form the product. Except in E2, not necessarily. And I'll come back to that. In E1, if your beta carbon has a hydrogen, it could be lost. Not necessarily the case in E2. So I'll come back to that. So what's the difference? Well, this is bimolecular. And so far, how many molecules of reactant do I have? 1. So I need a second molecule. What's that second molecule going to be? It's going to be a strong base. And that strong base I'm going to call B- for the moment. So that's the second molecule to make this bimolecular. Now, in the E1 mechanism, you form the carbocation, the H+ just kind of falls away, it combines with something else in solution, but there's nothing actively ripping that hydrogen out of there. Not so in E2. In E2, the base's role is to come in, take a beta hydrogen, and start the process. So the difference here is that the base is an active player. That's why it's E2. So the base could come in and grab HA. If it grabs HA, the pair of electrons moves to form the double bond, and then a pair of electrons goes to the leaving group. What would the transition state look like? Well, I'm going to set the molecule up here, and I should probably just write the final product here so that we can do our averages of charges. So I'm going to have a CH, the CH double bonded to the CH, and then a CH3 plus, the base with the hydrogen, and the Cl minus. That's going to be the final product. So what's the transition state going to look like? What bonds am I making and breaking? I am forming a BH bond, therefore partial bond. I am breaking the CH bond, partial bond. I am forming the CC double bond, partial bond. And I am breaking the carbon-chlorine bond. So the partial bonding scheme looks like that. Base grabbing the hydrogen, double bond forming, chlorine leaving. Where do the partial charges go? So what partial charge where? Partial negative on chlorine and
partial negative on the B.
And partial negative on the B, on the base.
Why do you have the bond, like the bond made between the hydrogen and the base like that? Like, why isn't it connecting to the... Wait. Oh, I see.
That's the bond that's being formed. So that's what the transition state's going to look like for an E2 reaction. What's going to change is the specific base and the specific molecule. But that's going to be how the partial bonding scheme goes. So I'm not going to give you a take-home quiz today on writing E2 and E1, but that'll come on Friday probably. And when I do, then you can go back and refer to this. Because that's how I intend the first time you do a mechanism. I mean, it'd be great if you could do it on your own without referring back to the notes. But if you have to refer back to the notes, refer back to the notes instead of just making stuff up. Okay. So there's our transition state. The hydrogen's leaving as basically an H+. But if we observe our rules about the average between reactants and products, there really aren't any delta positives in this transition state. And there's certainly no carbocation being formed. So that would be the first transition state to form product A. And then we could write the transition state for forming product B. Bless you. So it's going to be the same principle. The base is pulling the hydrogen off, only this time it's going to pull off HB on the end. Partial double bond forming, partial bond to the chlorine as it's leaving. and partial charges again. Delta minus on the base, delta minus on the chlorine. Okay. And that's going to form product B. So the real difference between E1 and E2 is that E2 has a base that's actively ripping the hydrogen off and starting the process, whereas E1 starts the process by forming the carbocation, which is the same first step as SN1. And so on Monday we said if you have SN1, you're going to also have a little bit of E1. But there are some other differences between E1 and E2 that we're going to get to. All right, so is everybody kind of with me here? In terms of...
Say it again, please.
What did I say?
Think about E2 and E1.
The difference between E1 and E2 is E2, the base is actively taking the beta hydrogen away. It's part of the rate determining step, because this is a one-step mechanism, just like SN2 was.
Does it always yield two products?
It's going to depend on how many beta hydrogens you have. So you could end up with 3 products if you had, because the carbon could be attached to 3 different things other than the leaving group. So you could end up with 3 different products. It's going to depend on when you remove a beta hydrogen, do you get a new product? And in order to determine that, we have to remember how to name alkenes. So this is 2-butene, and this is 1-butene. And so since they have different names, different products. So each problem is going to be unique. How many products do we get? And then we'll have to determine the major product. Okay. Okay. So let's go to what's the major product of this reaction? Well, let's review. So, in E1, what would the major product of this reaction would it be? Would it be A or would it be B? So, in E1 that we did on Monday, which one of these two would be the major product, A or B? Right? Should get 100%. Why not? Should be 100%. Let's put a pressure on me. Okay. A is the major product. According to you. Why? Why would say the major product?
More stable.
It's more stable. It's more stable because it's more substituted. So in E1, that's how we determine the basis of the major product. In E1, The major product is the most stable product, which is the most substituted product. Okay, and that's A in this case. Now, in E2, if you said, well, what's the major product in an E2 reaction? I'm going to say, it depends. And then you're going to say, on what? So what's it depend on? Well, it's going to depend on the nature of the base. Because right now we just have this generic strong base. So now let's talk, well, we can do this. Let's talk specifically about bases. What kinds of bases can I use? And then we'll talk about the stereochemistry of this reaction. I can switch it up. I don't have to do exactly what I did this morning. I'm a trained professional. So let's talk bases. So the kind of strong bases that I need to use for an E2 are things like alkoxides. An alkoxide is a deprotonated alcohol, or an amide. An amide, not to be confused with the functional group amide with the N attached to the carbonyl. This is a different kind of amide. N minus. So these are pretty high on our basicity chart, right? Only thing higher than N minus is a C minus or an H minus. We'll use that next semester. So, actually, no, we'll use it this semester, the H minus. So these are strong bases. They're both very strong bases. But here's the problem. The problem is strong bases are also strong no. Strong bases are also strong nucleophiles. Okay. They're negatively charged, so they're electron rich. So electrophiles out. So they're nucleophiles. So strong bases are also strong nucleophiles. So if I'm trying to do E2, and my strong base is also a strong nucleophile, it could do SN2 as well. And so what we're going to do is we're going to choose two extremes. For instance, CH3O minus, this is called methoxide. Methoxide is not an extreme. Methoxide's in the gray area. Is it going to act as a nucleophile or is it going to act as a base? All right, if I give these things human characteristics, which we often do, they have a split personality. So the first thing they try and do is act as nucleophiles and attack and kick off a leaving group. If they can't do that, let's say they get angry and they rip off a beta hydrogen to form the alkene. So their first tendency is to act as nucleophiles, and then, if they can't, they act as a base. So what I want to do is I don't want to live in the gray area right now, because that's just going to cause too much confusion, and there's already enough confusion that's possible. So I'm going to take my alkoxide, and I'm going to take away its nucleophilicity. And the way I'm going to do that is by remembering that in an SN2 reaction, that steric hindrance plays a huge role. So if I want to take away a nucleophile's ability to be a nucleophile, let's make it sterically hindered. So instead of using methoxide, let's put a tertiary butyl group on there. And let's make this a tertiary butoxide. And so a tertiary butoxide, because there's a tertiary butyl group there, I've now all of a sudden taken away its ability to act as a nucleophile. because it's too sterically hindered. And so now I force it to be a base. I force it to be a strong base. And there are lots of sterically hindered bases that you can use to use this approach with. Tertiary butoxide is the one that we're going to use. And tertiary butoxide comes in a number of alkali metal flavors. There's lithium, there's sodium, there's potassium, there's even cesium, if you want to live dangerously. Because you've all seen the alkali metals dropped in water and how they explode. Yeah, cesium just does that when you take it out of its glass. You just open it up and it explodes. That's why you need to keep it in like argon or nitrogen. Sodium, not bad, but as you go up the line, they get more reactive. In the most creative demonstration is somebody took sodium metal, they made a little boat out of it, they slid it down on Hot Wheels tracks into a kiddie pool where it exploded. That's creative. So the flavor we usually use is potassium. It has to have a counterion. Sometimes I'll put the potassium in, sometimes I won't. If you're not careful with potassium being a counterion, people show it everywhere. Like it ends up in the middle of a cyclohexane ring. It doesn't belong there. It belongs next to whatever the negative charge is. So oftentimes you won't see me put an alkali metal in. There's some other ones that your book may talk about. The sort of modern potassium tertiary butoxide is this nitrogen with two isopropyl groups. This is called LDA because it's called lithium, and this is diisopropyl amide. So it's lithium diisopropyl amide. That's more a modern day one. There's another one that I've used in research ever since I was at graduate school, and that's to take this nitrogen, add two trimethylsilyl groups on it, and you form lithium hexamethyl disilazane. Bless you. Really nice molecule because we can make all the flavors of it. We can crystallize it. We can purify it. We can even do NMR with it. So they all have the capability of being strong bases, but they're sterically hindered, so they're forced to be bases, not nucleophiles. So we're going to use potassium tertiary butoxide as our sterically hindered strong base. And so that's what this is going to be called. Now, that steric hindrance is going to play a role, and we'll come back to that. We're also going to use, at the other end, an NH2 minus. Now, there's something about NH2 minus that really does not allow it to act as a nucleophile. It prefers to act as a base. And what makes that, I'm not even going to venture to make up an answer to. It just doesn't act as a nucleophile. So we're going to use it as the opposite, our small, strong base. So I'm going to have two options here. I can use a sterically hindered strong base, or I can use a small base. And the reason for me doing that is because I'm going to be able to form different products using these two different bases. Okay. So those are the bases that I'm going to use: potassium tertiary butoxide and amide. Because my other option, using like methoxide as my small base, is going to get confusing because the methoxide will act as a nucleophile, whereas NH2 minus will not. Okay. So those are the bases that we're going to choose from. And then we'll come back and talk about methoxide. We'll make it more complicated as we go along next semester. Okay, so we've got our choice of bases. And so now we go back to our reaction and we say, okay, I'm going to do this reaction. I need to know what the major product is. Is it A or is it B? Well, that's going to depend on the base. How is it going to depend on the base? So let's rewrite this reaction. With our two beta hydrogens, HA and HB. And we still know that product A is still the more stable product. And product B is still the less stable product. But using these two bases, I can actually pick and choose what product I want to make. And that's going to be kind of a theme throughout the rest of the year. There's two branches of organic chemistry. There's people that study mechanisms, which is called physical organic chemistry. So physical organic chemistry has all of the love of physical chemistry, which usually that word love, physical chemistry doesn't go together. It's usually another word that goes with it. And organic, and there's not a lot of love in organic chemistry either. So you combine two of the most favorite topics, kinds of chemistry, and you put them together, and that becomes mechanistic chemistry to try and figure out how reactions work, which is what I am. I'm a physical organic chemist by training. Then you have synthetic chemists who basically their job is to make things. And sometimes they study a mechanism along the way, but usually they're interested in making things. And that's perfectly fine, because that's how you synthesize drugs, that's how you synthesize plastics. If you got a drug that'll cure cancer, somebody's got to figure out a way to make it. And so that's what synthetic chemists do. Well, in order for synthetic chemists to have the maximum tools in their toolkit, we need to be able to form sort of the yin and the yang of the reactions. If I use this reagent, I get this product. If I use this reagent, I get the other product. So that way we can control what product we're making. And so this is kind of the first example of this. Is if I want to form A, I need to use one of those two bases. If I want B, I need to use the other. And so we're going to talk about that over and over again. You do this if you want this product, you do this if you want the opposite product, let's say. So, let's talk tertiary butoxide first. If I have a tertiary butoxide ion base, which hydrogen is it going to have an easier time getting to? HA or HB? How many people say A? B. Why B? Why B? Dylan? It's a primary hydrogen. Primary hydrogens, we can label hydrogens the same degree as their carbons. So HA is a primary hydrogen, HB is a primary hydrogen, HA is a secondary. Okay. If you're still having difficulties with primary and secondary, we need to resolve that because we're using that over and over again. It's going to become second nature, hopefully. So that means the primary one is less sterically hindered. And so it has an easier time, quote unquote, easier time getting to HB. Well, let's be a little more specific here. Reaction coordinate diagram. because that's specific, right? Chemistry runs on energy. You want to know why something happens? You need to know the energy. Everything else in life is usually about money and power. But in chemistry, totally about energy. So what I have is I actually have a reaction that goes through two different transition states. One higher in energy than the other. So my question is, which one of those two transition states, the transition state where the tertiary butoxide is pulling off HB, or tertiary butoxide is pulling off HA, which one of those two transition states is going to have the lowest energy? Don't answer. But which one of those two transition states, when tertiary butoxide pulls off HB or HA, which one of those is going to have the lowest energy? So your choices are HA or HB. Which transition state is going to have the lowest or the lower energy? When it pulls A or when it pulls B? Because what I want to do is I want to put an A and a B on each one of these two transition states. Going once. There. Oh no, we're split. You know what that means? That means I save the question and you have 1 minute to discuss with your neighbor what you had and discuss, and then we'll revote. The question is which, when you write when you remove either HA or HB with tertiary butoxide, which transition state has the lowest energy? When the O partially bonds with HB, or when it partially bonds with HA? That's the question. So when the tertiary butoxide, if I wrote the two transition states of the O minus coming in and grabbing HB, or the O minus grabbing HA, which one's going to have the lowest energy? Which transition state is going to be more stable? Okay? We're not to that point yet, so let's just look at it from the perspective of primary, secondary. Okay, so time to revote. Yeah, I want to put an A or a B here, and I need to know Which one goes here on the lower transition state? The lower energy transition state. Is that A or is that B? Okay, everybody's answered. All right, there's a movement towards B. A significant movement towards B. So why did anybody who voted for B? Why did you vote for B? Or if you want to make a case for A, make a case for A, Peter.
So B is a primary and it's more reactive, so it's more likely to hydrogen, and I believe it's like less sterically hindered, so it'll be easier overall to take the hydrogen.
All right, let's start your answer at less sterically hindered. And let's not worry about the first part of the answer. So HB is less sterically hindered, so that means when the O- is partially bonded to that hydrogen, you're going to have like less steric hindrance overall. It's going to have a lower energy. What happens if I'm partially bonded to HA in the middle of the molecule? That tertiary butoxide is going to have more steric hindrance. It's going to be closer to the other groups. It's going to have a higher energy. So the transition state for pulling off the hydrogen B is going to be lower. So this is the A transition state. This is the transition state for forming B. Okay, does that make sense to everybody? What I'm doing here is I'm putting a very specific term. Instead of saying it's easier, the true answer is it has a lower transition state energy. And what do we know about lowering the transition state energy makes the reaction go faster? Notice I haven't used the word Hammond, nor will I. Okay, now I heard some discussion about products. B is still less stable than A, or A is still more stable than A. So the reaction coordinate diagrams look like that. That's not normally the way we do it, right? Because we've got Hammond's postulate where we talk about, oh, well, since the product's more stable, the transition state's more stable, but that is not the case here. What is the case is that the steric hindrance in primary versus secondary, or lack of steric hindrance, is what's forcing this reaction to form B. So in your book, they talk about a kinetic product. And I seem to remember we talked about kinetic and thermodynamic products using the typical first reaction where we learn about that, which is a second semester reaction. I remember we talked about that a while ago. But one of the things I've learned is a while ago could be Monday. And so when we've talked about stuff a while ago, we need to talk about it again and again and again. So this is what we would call sort of a kinetic, I guess it would be called the kinetic product because it's formed fastest. Why? Because it has a lower transition state energy. If you do remember us talking about it a long time ago, well, good for you. But in that case, what we had was we formed the kinetic product and then it reversed itself and went back to the middle, and then there's no reversibility here. Once you form the kinetic product, you're done. So when I looked in the book and saw kinetic, I'm like, why are they talking about that? This is why. So this is essentially a kinetic process. It's dependent on the transition state of the reaction, not the product energy, not the stability of the product. And that's new for us. Right? That's something new for us.
Wait, didn't we, like, a long time ago when we were talking about the reactions?
A long time ago, it was like a month, but yes.
Like a month ago. Didn't we say when it was the product was more stable, like that would have a higher energy transition state to create a more stable product?
Typically, that's how it works, but this is a new reaction. So
not
this
like-
is a different one. It's not like those ones we've done in the past. So Hammond's postulate does not apply. Does that kind of, so, this is the true energy. If you want to just say, oh, well, if I'm a large base, I can get at the less sterically hindered hydrogen faster than I can get at the more sterically hindered hydrogen. Same thing, except it's not invoking an energy coordinate diagram. Now let's talk about the little base. The little base can get to both. And it can get to both probably equally as well. And so what's that? So this is the tertiary butoxide coordinate diagram. The one with the NH2, the transition states are going to be nearly identical. But in this case, you have product B, and you have the more stable product A. So what happens here is, this is what the book would call thermodynamics, because in this case, because the transition states are nearly the same, we're going to form more of the more stable product than the less stable product. Okay. So and again, if you just want to think size, common sense, small base can get to both. It's going to remove the hydrogen that gives you the more stable product. So this gives us the ability then, using those two bases, to form the product that we want. Do I want to remove the hydrogen that's least sterically hindered? If so, use a big base. Do I want to form the more stable product? Use a small base. And notice, I'm very specific in the way that I say that. I didn't talk about the product stability there, except to say the most stable product. I did not say the least stable product or the least substituted product. Now, 9 times out of 10, if you're removing the more sterically accessible hydrogen or the least sterically hindered hydrogen, you will get the least substituted product. But that's 9 times out of 10. So there are cases where it may not give the less substituted product. Right? If it's 9 times out of 10, the one times, that's what I'm going to put on the test. Right? So you don't want to work too much in rules. What?
What did you say for using the larger?
If you want to remove the hydrogen that's less sterically hindered, use the big base. If you want to form the more stable product, use the small base. Now, there's one caveat to all of this, and that is there is a geometric restriction on an E2 reaction. And here is the geometric restriction. The hydrogen that's being removed, the beta hydrogen, must be anti-periplanar to the leaving group. So here I've drawn it anti-periplanar to the leaving group. Of course, if I was over here, looking this way, here's the hydrogen, there's the leaving group, and we would say the hydrogen and the leaving group are anti. And the periplanar is understood. Some sometimes it's anti-coplanar. I just call it periplanar. So when the hydrogen must be anti-periplanar to the leaving group for it to be removed. And we'll talk about the consequences of this for acyclics and cyclic molecules on Friday. But that's what it has to look like. So that means if the hydrogen is not anti-periplanar, it's not being deprotonated. So it's got to look like this. Why? Well, this is going to kind of you have to be creative on this. At least I have an animator program on my iPad that I can draw step by step, and it'll animate everything. But like that's going to happen between now and Friday. Maybe it will. So here's what I'm doing. I'm converting that set of orbitals, those two sp3 orbitals, including their little tiny guys that we never worry about except now. Those are being converted to two p orbitals, 50-50 lobes, parallel to each other. So what happens as the hydrogen, so let's see, they're in this orientation. So as the hydrogen is being removed, and as the leaving group is leaving, those two orbitals swing up together to become parallel to each other. And then you've got a p orbital, then you've got two p orbitals parallel to each other to make the pi bond. Okay, so they have to start out periplanar because that's the least amount of movement for them to swing. And the least amount of movement means lowest transition state energy. Because every time you got to move something or rotate something, it costs energy and it jacks up the energy of the transition state. Now, what I cannot do with two arms here is I cannot, as I'm swinging my arms to become parallel, there's also down here, the little lobe is growing in electron density. So that by the time they come here, it's 50-50. And at that point, what I actually have is I've got a p orbital with two electrons, an empty p orbital. They now overlap with two electrons, and I form the pi bond. So I cannot, the transition state, in order to form the lowest energy transition state, those two orbitals must be periplanar, and it must be such that the hydrogen is up here and the leaving group's down here for those lobes to grow appropriately.
If they weren't anti-periplanar, could you do like a ring flip and then make them?
Well, we'll talk about rings, and the answer is yes. If possible, we might have to do a ring flip in order to make them. Or in an acyclic system, we're going to have to rotate the hydrogen until it becomes anti-periplanar. But the only way the double bond forms is when that hydrogen is anti-periplanar to that leaving group. That's it. So on Friday, where we'll start is, why wasn't this an issue with carbocations, with SN1? And the reason is because once you form a carbocation, all the hydrogen has to do is be periplanar to the empty lobe. It doesn't matter what side it's on. Okay? If you're overwhelmingly curious, since I flipped these two topics, I actually did this with a little bit more time this morning. So if you go on the YouTube page, you could watch that part. But otherwise, we'll start here on Friday. Okay? So as always, if you have questions, stop by, email me. Otherwise, I will see you on Friday.